Scientists have unearthed a vast subterranean water reservoir nestled within the Oregon Cascade Mountains, holding a volume exceeding twice that of lake. The aquifer is estimated to contain at least 19.4 cubic miles of water, equivalent to approximately 162 trillion individual bottles. To put that in perspective, consuming one bottle daily would necessitate around 444 billion years to deplete the entire supply. The scale of this underground reservoir renders its discovery remarkable. The Cascade Mountain Range, renowned for harboring the planet's largest aquifer, extends approximately 700 miles from Northern California into British Columbia. Within Oregon, the high Cascades feature younger volcanic formations dating back roughly 8 million years. In contrast, the Western Cascades are significantly older at 45 million years, characterized by deeply carved canyons and valleys. Scientists are focusing their research on the transitional zone between these regions to decipher the processes of water movement through volcanic rock and the geological evolution of volcanic activity over extended periods. During this research, scientists were measuring rock temperatures at varying depths when a remarkable aquifer discovery was made. The expected temperature rise with increasing depth due to proximity to the Earth's core was not observed. Surprisingly, in specific areas, the temperature remained constant even at considerable depths. This thermal anomaly provided strong indication of water coursing through the rock matrix, effectively cooling it. In essence, the Cascades serve as a natural water tower, accumulating and gradually releasing water into nearby rivers and streams. These geological water findings bear significance for two primary reasons. First, they present a potential water source for the future. The sheer magnitude of the subterranean water reserve suggests a valuable resource. However, the long-term stability and resilience of this resource to environmental changes are currently unknown. Therefore, further research is essential to ensure responsible management and utilization. Secondly, the aquifer influences volcanic activity. When water penetrates deep underground and encounters magma, it rapidly transforms into steam, generating extreme pressure that could instigate explosive volcanic eruptions. A comprehensive understanding of the water volume stored within volcanic rock is crucial for predicting future eruptions and assessing the associated risks. Despite the excitement surrounding this discovery, numerous questions remain unanswered. For instance, the mechanisms governing water movement through the volcanic rock and the proportion of water accessible as a usable resource require further investigation. Given the aquifer's dependence on precipitation in the form of rain and snow, prolonged periods of drought could have severe repercussions for both water supply and volcanic equilibrium. Researchers are actively investigating the total impact of the Cascades volcanic water reservoir and formulating strategies for its responsible management. Consider the geological phenomenon that is the Cascade Range, a massive mountain range spanning from Northern California to British Columbia, bisecting Oregon. Within Oregon, the range extends roughly 260 miles in length and up to 90 miles in breadth, encompassing 17,000 square miles, an area larger than any of the 9 smallest U.S. states. Notably, the Oregon portion of this mountain range is largely of volcanic origin and contains at least one area where water is stored in volcanic rock. The formation of this range is attributed to the Cascadia subduction zone, or the Juan de Fuca tectonic plate, a section of the Earth's crust located beneath the Pacific Ocean, is gradually forced beneath North America. As the plate descends, the intense heat and pressure liberate water from the oceanic rock, reducing the melting point of the surrounding mantle and generating magma. This magma rises to the surface, fueling the Cascade volcanoes, and forms a part of the Ring of Fire. The Cascade Mountains in Oregon, while seemingly individual, are actually a segment of a far broader volcanic network encircling the Pacific Ocean. This immense zone is in continuous flux, reshaping and redefining the landscape. The Oregon Cascades themselves are composed of two distinct geological regions, the Western Cascades and the High Cascades, each possessing unique characteristics and origins. The Western Cascades represent the older section, originating around 45 million years ago. Over eons, these mountains have been sculpted into a rugged terrain, deeply incised by rivers. The erosive power of these waterways has carved canyons. Some plunge into depths of approximately 3,700 feet. This region was once characterized by active volcanism, but over vast spans of time, erosion has become the dominant force, continuously altering its appearance. Conversely, the High Cascades are a much more recent formation, exhibiting considerably less erosion. Around 8 million years ago, volcanic activity shifted eastward, leading to new eruptions that filled ancient canyons, thereby creating a smoother, more uniform terrain. In this area, rivers haven't had the extensive time frame needed to excavate deep valleys, unlike their counterparts in the Western Cascades. Consequently, a side-by-side comparison reveals a stark contrast. The Western Cascades appear jagged and deeply dissected, while the High Cascades exhibit a more even, built-up appearance. Several of Oregon's most renowned volcanoes are situated within the High Cascades, including Mount Hood, Mount Jefferson, the Three Sisters, and Crater Lake. Crater Lake, notably, was formed by the cataclysmic eruption and subsequent collapse of Mount Mazama. Unlike smaller, ephemeral volcanoes that erupt briefly and disappear, these colossal volcanic centers have maintained activity over millennia. This prolonged activity has fostered intricate magma systems capable of producing a wide spectrum of lava types, from fluid basalt to andesite, dacite, and rhyolite. Rhyolite magma, in particular, is associated with potentially enormous explosive eruptions. Consequently, while some volcanoes may exhibit relatively gentle fusions of lava, others possess the potential for catastrophic blasts. A significant attribute of these enduring volcanoes is the sustained high temperature of their subsurface magma chambers. This feature positions the Cascades as a prime location for harnessing geothermal energy. Substantial quantities of heat reside beneath the surface, awaiting extraction and utilization. Moreover, the Cascades also function as a significant volcanic water reservoir, with undetermined potential applications in the future. As previously noted, the Cascades are part of the Pacific Ring of Fire, a zone of intense geological activity. This massive horseshoe-shaped region encircles the Pacific Ocean, spanning approximately 25,000 miles. It is one of the Earth's most dynamic areas, characterized by constant shifting, collision, and grinding of tectonic plates. These interactions give rise to potent earthquakes, volcanic eruptions, and deep oceanic trenches. The Ring of Fire traces the boundaries where multiple tectonic plates converge, surrounding the vast Pacific Plate. These plates are not static. They are continuously moving, either colliding with or sliding beneath each other at fault lines. This dynamic interaction results in a range of geological phenomena, from deep-sea trenches to towering volcanoes and violent seismic events. One of the most extreme illustrations of this is the Mariana Trench, located east of Guam. Reaching a depth of about 36,000 feet, it represents the deepest oceanic trench on Earth. It was created through a process known as subduction, where one tectonic plate is forced under another, sinking into the Earth's mantle. The Mariana Trench remains one of the most mysterious regions on the planet. It was once believed that the extreme depths of the ocean were devoid of life, but this notion was disproven in 2005. Researchers discovered a minute, single-celled organism residing in the Challenger Deep, the most profound section of the Mariana Trench. The expedition also unearthed vibrant, rocky landscapes and peculiar sea cucumbers. The Mariana Trench features hydrothermal vents, essentially underwater geysers. Despite the scorching and acidic conditions surrounding these vents, unique organisms and microscopic beings thrive there. Additionally, the Ring of Fire is the source of approximately 90% of the world's seismic activity. The region has experienced some of the most devastating earthquakes ever recorded, including the 1960 Valdivia earthquake in Chile, which registered a colossal 9.5 on the Richter scale. Beyond seismic events, the Ring of Fire is also characterized by a high concentration of volcanoes, accounting for around 75% of the planet's total. Some of history's most notable volcanic events have originated within the zone, such as the eruption of Mount Tambora in Indonesia. In summary, the Ring of Fire represents one of the most perilous locations on the globe, while also presenting a realm of intriguing scientific inquiry. The potential for additional discoveries remains significant, as exemplified by the discovery of a massive water reservoir in the Cascades. If this exploration has satisfied your curiosity, please show your appreciation by endorsing this content and distributing it among your acquaintances. For additional information, select the suggested videos.